The law of the conservation of energy and application in an amusement park. This is a very complicated problem based on a very simple law, the law of the conservation of energy. The beginning energy equals the ending energy. In this particular problem, we'll assume no coefficient of friction, that the roller coaster ride has absolutely no friction and there's no energy losses due to friction. Make sure you have a piece of paper and pencil and you can follow the derivation of the equation that I used to solve the problem. Make sure you have a calculator. Stay ahead of the game and make sure you understand each step. If you have a problem or question about any of this movie, write down the question and ask me in class. In an amusement park, a 500-kilogram car rolls down one hill and up another. The diagram below shows the motion of the car rolling from left to right. When the car reaches point A, it is moving 12 meters per second. The height of the hill A is 60 meters and hill B is 35 meters. How fast is the roller coaster going at point B? Now, again, we will assume no energy losses, that the problem is actually as straightforward as it appears. A question is, will the mass play a role in the solution to the problem? If the roller coaster car had a mass of 1,000 kilograms, would that be significant? If it had a mass of 250 kilograms, would that be significant? If so, if not, why? The law of the conservation of energy states that the sum of the initial kinetic and potential energies is equal to the sum of the final kinetic and potential energies. We know that delta KE plus delta PE equals 0. Delta KE equals the additive inverse of delta PE. If you expand delta KE and delta PE, you get the final kinetic energy minus the initial kinetic energy will equal the additive inverse of the quantity final potential energy minus initial potential energy. Distributing the additive inverse sign, we get final kinetic energy minus initial kinetic energy equals negative final potential energy plus initial potential energy. Then simply rearranging the equation D, we get equation E multiplied through by a -1, and we get the equation which is consistent to the law of the conservation of energy, which states again that the sum of the initial kinetic and potential energies is equal to the sum of the final kinetic and potential energies. That's where we will begin. Equation H is the same as equation G. That is, the initial kinetic energy plus the initial potential energy will equal the final kinetic energy plus the final potential energy. Expanding kinetic energy, 1/2 mv squared, where you have initial velocity, and the initial potential energy, mgh, where h is the initial height. That will equal the final kinetic energy, 1/2 mv squared, where it's v final, and the potential energy final will be mgh, where the height is final, hf. The mass is the same throughout and can be factored out. So you see that when I asked before, is the mass of the car on the roller coaster relevant? And the answer is absolutely not. And equation J justifies that. Equation K is the resultant equation. 1/2 V naught squared plus GH naught equals 1/2 VF squared plus GHF. I'm trying to calculate V final in equation L, which is the same as equation K on the former slide. Now, the term 1/2 VF squared is the term I wish to isolate. So if I subtract GHF from both sides and then simply flip the equation, I get 1/2 VF squared equals 1/2 V naught squared plus GH naught minus GHF. Now, multiply both sides by 2, and I wind up with equation O. 2 times the quantity, 1/2 V naught squared plus GH naught minus GHF. Taking the square root of both sides, I finally get VF equals root 2 times the quantity, 1/2 V naught squared plus G times H naught minus HF. Now, all that you need to do now is to identify the knowns and the unknowns and then plug in. I have identified the knowns and the unknowns. V naught is 12 meters per second. G, the acceleration due to gravity, is 10 meters per second squared. H naught is 65 meters. HF is 35 meters. The unknown is VF. The original equation is delta KE plus delta PE equals 0. Make sure you go back to the original problem and identify the knowns and the unknowns and make sure they are consistent with what I have listed here. The equations below, Q and R, Q being the same as P on the former slide, represent the completion of the problem pretty much. What is only left in R is to plug in the values from the table above and then simply calculate. Make sure that you verify the calculation of R on the succeeding slide. Again, if you have any questions, write them down and see me in class. I have plugged into equation S, reduced equation S to equation T, and solved for V final in equation U. Make sure that you can make this calculation. If you can't, write down what it is you are having a problem with and ask me in class. Please go through the movie again, making sure you understand each slide. Pay specific attention to the derivation of the equations, and again, write down anything that you do not understand.